Hey everyone, in this video, I will walk you through the full workflow from capturing a 3D scan with the LiGrip O2 LiDAR scanner to turning that data into a CAD model. This is a real commission project where the architect firm brought me in to perform a 3D scan and build a precise CAD model of the building. The architect will use this CAD model to redesign the old bank building into a franchise restaurant. They need precise data to determine which parts of the structure can be kept and which should be demolished. From scanning to delivery, the entire process takes less than 24 hours. Let's kick off the 3D scanning. I'm starting outside where I got full GPS reception, and I will point the scanner toward the building to initialize. After initialization, I walk a small closed loop. This creates a slab loop while maintaining full GPS reception, and in just a moment you will see that by doing this, the building's floor slab comes out perfectly level straight from the scanner. No manual adjustment needed. On this side of the building, the semi-open area causes the scanner to lose their fixed RTK solution, but with the LiGrip O2, that's not an issue. It's automatically switched over to slab mode. And here is the standout feature of this LiDAR scanner, RTK Fusion. You can start outdoors with GPS reception, scan just half a minute, then move inside. No matter how complex or large the indoor space is, the entire scan still comes out fully georeferenced. When I go through a narrow doorway, you will notice I turn sideways this way. The scanner can capture both walls at once, ensuring proper tracking. This room has reinforced concrete walls. It must have been the vault. The walls are particularly thick, and a SLAM LiDAR scanner is the perfect tool for measuring slab thickness. This room is completely dark. The power's been cut and I forgot my flashlight. It doesn't affect the scan quality, but the point cloud colors in this area will all appear black. I have already scouted the area before starting the scan and made sure all the doors are opened. This is an important step. Always keep doors open before scanning. This bathroom is very small, so instead of walking in, I just stick my hand in with the scanner. That's enough to capture all the data. Now I'm looping back outdoors. Throughout this scan, I have created several smaller closed loops which help collect drifting alerts. You will see the result in the point cloud. Both the exterior and interior wall lines stay perfectly parallel. Before ending the scan, I wait until the RTK regains a fixed solution, then point the scanner toward the same spot where I started. This scan took just 8 minutes at a rate of $1 per square meter. That means I earned about $1,400 from this project. In LiDAR360 MLS, the processing took 34 minutes. Soon, Green Valley will release cloud-based point cloud remapping, so you won't need a PC to handle the processing anymore. You can simply upload your scan data to the cloud, and by the time you arrive at the office, the colorized point cloud will be ready to download. This is a great feature because your PC won't be locked up during point cloud processing, and that way your workstation stays free for something more productive like CAD modeling. This is the accuracy error report. Some scan data in the smaller loom shows lower accuracy, but overall 60% of the data falls within 1 centimeter of error. These yellow dots mark the positions where RTK accuracy surpassed the SLAM path. The software used those points to position the trajectory instead of relying on the SLAM. Here in Cloud Compare, I'm checking the building floor level. Without RTK, most SLAM LiDAR scanners use the floor where the scanner was initialized as the reference plane. So if the floor isn't level, the entire scan dataset will also come out unlevel. You need to adjust the building's floor level so it's parallel to the XY plane using Cloud Compare. But when you scan with RTK Fusion using the LiGrip O2, the interior floor always comes out perfectly level. This allows you to import the scan data directly into CAD software without having to manually level it first. So I will use Cloud Compare to crop out any unnecessary scan data. After cropping, I'm left with 120 million points, about 4.2 GB in size. Once remodeled in CAD, the file size drops to just 1.5 MB, which is even smaller than a photo taken on your mobile phone. Now we move on to the most important part of the process, reverse engineering. Most clients don't accept raw 3D scan point clouds as deliverables. They require CAD files, either 3D models or 2D drawings. This step is the key to turning your LiDAR scanner into a profitable tool. I will also create a slow-paced tutorial version of this video, and I will include the code file link in the description once the tutorial is ready. Here in BricsCAD, when your scan data contains GPS coordinates, the y-axis automatically points north. You can also enable the Google Street Map overlay to trace loads and create accurate load maps directly in your drawings. After tracing the load for mapping, I move the office floor level to ground zero. This is the highest elevation of the entire floor slab, while the road sits at the lowest. The first step in creating a building model is to start with the floor slab. I will trace the entire slab boundary at ground zero level, covering both the interior and exterior. The construction quality of this building isn't very good. The orthogonality of this decorative column grid line is 0.3 degrees off from a true right angle. I have set BricsCAD to display only 5 million points from the cloud, so the viewport remains extremely fast and responsive during line tracing. This is how BricsCAD runs fluidly even when opening a large point cloud dataset. In BricsCAD, the point cloud is automatically decimated when you zoom out, and more detail appears as you zoom in. You can see the scan's precisions from the thickness of the point cloud wall lines. They are sharp and extremely thin, which makes line tracing fast and effortless. I have worked with the scan data from the more expensive terrestrial LiDAR scanner, the LiDAR360, and the scan quality from the LiGrip O2 is actually better. Next, I'm going to extrude the floor boundary down to the lowest point, which is the road level. BricsCAD Auto Boundary Detection makes extrusion extremely fast. This building has two types of floors: suspended slabs that sits on the foundation and slabs on grade. The latter are a bit trickier to model because they are not perfectly level and often lean across one or two planes. To create the lean angle of the slab on grade, I use the slice command to shape each slab individually. For this part of the dirt ground, I create a sketch profile to cut out the ground level contour. The footpath also runs along the road level, so I need to divide it into segments and slice each one individually. When creating floors, whether suspended or slab on grade, it's best to avoid curved surfaces. Using slice plane is the recommended practice, since curved surfaces are less useful and can't serve as reliable reference planes. The entire floor area is 1,400 square meters, with many detailed shapes at varying elevations. To get the CAD model as quickly as possible, you need two things: clean scan data and efficient CAD software. In my 27 years of experience, BricsCAD is one of the fastest building modelers. It may not be the fastest building design tool overall, but it's certainly the fastest and easiest for scan to BIM projects. Working effectively with 3D scan point clouds straight out of the box. Now the floor slabs are modeled, I move on to tracing the interior wall lines. You can see they are all perfectly parallel, an indication of precise scan data. The most consistent wall type are precast panels or drywall on the metal framing, while brick walls often show slight thickness variation from a mortar lender, usually around 1 to 2 centimeters. Next, I'm going to extrude all the walls up to the exterior ceiling level. The wall could be taller, but I can't specify dimensions that the scanner didn't capture. So when you scan from outside in or inside out, you capture the wall thickness value. The vault room has 200 mm thick reinforced concrete walls, and knocking them down could damage the building's main columns. This is a criteria factor the architect needs to know. This is why precise color mapping on the point cloud is essential. When creating cutouts for doors and windows, you rely on the color contrast in the point cloud to guide the geometry. This is how I quickly create a fixed glass panel that sits at the center of the wall depth. I use an extruded surface to split the wall, then push the solid face inward from both sides to equal depth. Now that all exterior wall openings are cut, I move on to the interior wall openings. BricsCAD Section View 2 lets you block out half of the wall, which is especially useful for creating sketches in tight spaces. This is how I quickly create the ceiling panel. First, I draw a rectangle and convert it into a surface. Then I use the imprint command to project the wall lines onto the surface. After exploding it a couple of times, I left with the cut panel, which I then extrude into a solid. Next, I adjust the ceiling height for each room individually. The vault room likely has a reinforced concrete ceiling, otherwise it would be far too easy to access the vault through the roof. Next, I'm going to model the roof facade. This facade is made of aluminum composite panels, essentially forming a hollow box that covers the metal roof. The only way I can scan the roof is with an extension pole. The pole reaches up to 3 meters with a 2 kg scanner, but handling anything taller becomes very difficult. Since the facade is 5 meters height, I couldn't reach it with the pole anyway. I can't model what the scanner doesn't capture, so I will leave it as a solid box. There's a house behind the bank building that I didn't walk over to scan, but thanks to the LiGrip O2's long capture range, the data is sufficient for me to model the entire roof. There are 6 power line poles to model, and some of them aren't standing straight. I had to use the loft command to create that geometry. There are some small trees in the area. I'm not going to model them one by one, so instead I use the library models and scale them to fit. Now that the 3D CAD model is complete, let's generate the 2D CAD drawings. BricsCAD has an automatic 2D drawing generation feature. From the 3D model, you can create as many projection or section views as you need, and they are generated in just a split second. In this project, I will generate 16 2D drawings. Doing this manually would take days, but with automatic drawing generation, it completes in seconds. The 3D CAD modeling shown in this video is the fastest and most accurate way to create a digital twin of a building. To get the most out of your LiDAR scanner, you absolutely need CAD skills. Because the model is aligned to true north, BricsCAD can generate sunshade simulations and predict shadow casting at different times of the day across any day of the year. This building is well designed for sunlight protection. The front stays shade and cool until about 4 p.m., which reduces the cooling load and saves a significant amount of energy. I have now reverse engineered 3 buildings using the LiGrip O2, and it has proven to be the best LiDAR scanner for scan to BIM projects. The precision and point cloud quality are excellent, and the RTK fusion feature is indispensable. It works flawlessly. The full video tutorial will take me a few days to produce, and it could be several hours long. Once it's ready, I'll post the link in the comments below. Thanks you guys for watching. I'll see you in the next video.